Hi and welcome to the Econ Experiment. In this video, we are going to talk about the multiplier effect, and we are going to try to understand this with the help of a numerical example and also how it's represented on a graph. So within the goods market, the multiplier effect, really what it's trying to say is that when you're increasing any component of the autonomous spending, then although this might be increasing by just 1 unit, but because of the presence of the multiplier, the final effect on the increase in production is greater than 1 unit. And in this video, we'll see how to visualize that on the graph, also how the equations imply this increase, and of course, we'll also see whether we can understand this with the help of a numerical example. So let's first start with the equations. Now, if you know how we represent equilibrium output in the goods market, you would know that there's actually an identity between total demand and production. And production comprises of C plus I plus G plus NX. But for simplification purposes, let's avoid this right now and say that we are considering a closed economy. You could, of course, do this entire procedure even when NX is available, but then, we can make simplifying assumptions without really affecting the final analysis of our model. And when we can do that, we should do that. So we'll ignore this right now, which means that this is what we're left with. Z equals C plus I plus G. Now, all of these three components that enter into the total demand or production equation have their own specifications, and they have certain assumptions placed upon them as well. So when we're talking of consumption, we say that this is the equation of consumption. This can be further simplified as this. So consumption comprises of an autonomous consumption part and then MPC times the disposable income. Then when we say when we're talking about investment, we say that investment is determined exogenously, that is outside the model. And since we do not have to specify anything about investment within the model, it does not really have any specific equation to it. We just say that investments are represented by the capital letter I. And then G is the government spending. Now, although government spending has two components, the G part, which is the spending part, which represents what goods and services the government is purchasing, and the T part, the taxes that the government is collecting. But here we do not explicitly need to write T, because if you notice, this automatically enters the equation when we are speaking of the consumption. So this is our framework of the equations. But how do we arrive at the multiplier from here? We do this by making some very generalized simplifications to the equations that we just discussed. So let's see how that is done. We are saying that Z equals C plus I plus G, or Y equals C plus I plus G. At this point, we have said that this is an identity, so we can write this interchangeably. Let's continue with this part of the equation. Then we simplify this. Now, what we really need to do is take all the Y terms on the left hand side and then keep all the other terms on the right hand side. So when you do that, I just opened the bracket here and then I carried C1Y to the left hand side. You get this. You take the Y term out and further simplification. Gives us this as the final result. So really, we haven't made any change to the equations here. All we have done is some simplification, and the simplification was to get all the Y terms on the left hand side first and then simplify the entire equation for Y. Now when we do that, we notice that there are two parts to this equation. One is the denominator, which is 1 minus C1, and the other is the numerator, C0 plus C1T plus I plus G. Now this part is the part that we refer to as the autonomous spending. Why autonomous? Because it does not depend upon income. And what is this part? This is our multiplier. Now let's look into this in a little more detail. So the multiplier is 1 upon 1 minus C1. And what is C1? We know that C1 is the MPC. And another fact about MPC is that it can be any value between 0 and 1. 0 and 1 are extreme cases where you are either consuming all of your disposable income or you're consuming none of it. And let's see how we can determine the multiplier based on the value of MPC, because what a multiplier really is the reciprocal of the difference between 1 minus C1. So first, let's take an extreme case where MPC is 0. When MPC is 0, your multiplier is 1. What does a multiplier 1 really imply? It means that if I increase the autonomous spending by 1 unit, because of the fact that it gets multiplied by the multiplier, and since the multiplier is also 1, my total increase in production or income is also 1. But what happens when MPC is some arbitrary value between 0 and 1? For example, let's take MPC equals 0.6. What is the multiplier then? The multiplier becomes 1 minus 0.6, which is 1 by 0.4, which is 2.5. Now, what does this mean? This means that if I increase my autonomous spending by 1 unit, the total increase in production is the multiplier times the increase in AS, which is really 2.5 into 1, so 2.5. So this means that even if I increase my autonomous spending by just 1 unit, my total increase in production is more than 1 unit, it's 2.5. So as long as MPC is greater than 0, and of course within the bounds, the increase in autonomous spending leads to a more than 1 factor increase in the total production or the total income. This was the concept of MPC with the help of a numerical example, and we will conclude this video by discussing how can we visualize this on a graph. So, well, this is how you plot stuff in the goods market. You have income on the x-axis, you have demand or the production on the y-axis. And we know that there's this equality between total production or total income and total demand, which is represented by this 45-degree line from the origin. Which basically what this means is that any point on the line, when drawn to the x or y axis, has the same value. So any point, if you trace it back, will have the same value, which is how it indicates the equality. But that's something that we don't need for our discussion right now. So I'll just quickly get rid of this. And we've plotted this relationship. Now we want the total demand to be on this graph. So total demand is a graph that is a line that looks something like this. And why does this have a y-intercept? This has a y-intercept because of the autonomous spending. The spending that takes place even when income is 0. That's what I meant when I said that it does not depend upon income. And then there is some spending that depends upon the income because of the MPC. So this is why we have a upward sloping line. And now we want to see what happens when there is an increase in autonomous spending and how does the multiplier come into the picture. So the increase in autonomous spending will be represented by an upward shift on the y-intercept. So let's say that the increase leads to the y-intercept coming up until this point. But we do not change the value of the MPC here. The MPC remains as it was. So this means that the slope of this line doesn't change, only the intercept changes, which means that this line just shifts upwards. So when it shifts upwards, it would look something like this. Let's name it ZZ dash. So initially you were at a point A. Now if you are at a point B, let's analyze what really happened here. So this was your initial position and now you're here. So when we're saying that an autonomous spending was increased, we mean that we move from the point A to a point C. Now, when there is an increase in autonomous spending, this means that there is an increase in income. Because we know that when there is an increase in production, that leads to an increase in income, which we represent by this horizontal shift. So from a point C, we move to a point D. And now I'll zoom in a bit so that we can understand a little better. Now, when there is an increase in total income, people have more money to demand more goods, which means that there is an increase in total demand. So then there's a movement upwards from this point till here. Let's call this E. And then again, because there is an increase in demand, there's an increase in production, and we have a horizontal shift, then again an upward shift, and this is how you move. So what I really wanted to explain was that although you started from a point A and you ended at B, it's not as simple as a simple jump. What is really happening is that you're first moving upwards, then horizontally, then upwards again, then horizontally, then upwards again, and horizontally, and then you're finally reaching your point B. And you notice that this is not a straightforward movement. There are oscillations in between. And because of these oscillations, these are where the multiplier effect actually comes into play. It multiplies every single movement, and therefore the 1 unit increase in AS leads to an ultimate increase of 2.5 in total production, which is of course greater than 1. This is how the multiplier really works. And we have discussed everything that we wanted to discuss in this video pertaining to the graph, the equation, and we've also discussed this with a numerical example. So this was all about the multiplier effect. And we will conclude our video here. So if there are any other topics that you would want me to make videos on, please let me know in the comments. And if you like this video, please subscribe to my channel. Have a good day.